So who is the father of game theory? Well, John von Neumann, you should say, right? 1928, the min-max theorem, it all started from there. In fact, if you go back 7 years, you'll find a paper by Émile Borel where he introduces quite a bit of the ingredients of modern game theory, including a game known now as the Blotto game. So this game is between two players, and they're competing for some battlefield. Now, each player has a budget of troops, and the purpose of the game is to allocate those troops across the battlefields. And then it's a winner-takes-all situation. The way utility is computed, you just look at the value of each of those battlefields and sum them up. So this game, since its introduction more than a century ago, has received quite a bit of attention, but surprisingly, not all of the cases have been actually solved. So where does the difficulty come from? Well, since you're going to be playing a mixed strategy, each allocation to each battlefield is a random number, but you have to find a collection of numbers that add up to a deterministic number t, which is your budget. And that's what makes the problem difficult. In fact, if you relax this to having only this constraint in expectation, then you can find explicit solutions. So now the question we're asking is, well, given those marginal strategies, can you couple them in such a way that their sum is deterministically equal to your budget? And the answer is yes. It comes from joint mixability, but in fact this is only an existential result, and what we're asking is how to do it, and our solution is obviously going to be algorithmic. Our approach consists in first reducing the problem to 4 battlefields, because coupling between n battlefields is exponential in n in size, and that's not desirable for us. We want polynomial time algorithms. And then we apply single iterations to find a feasible coupling. This translates into nice time complexity to find epsilon optimal strategies when they exist, or epsilon Nash equilibria.